start. So I am very happy to start our first seminar this year. It's kind of like different than usual, and I'm sorry we don't have cookies. Our speaker today is a great speaker, is Jianqing from who is Frederick C. Moore Professor of Finance and Statistics and Operation Research and Finance and Engineering at Princeton University, where he also chaired the Department of Operation Research Financial Engineering. He won many awards, including the COPS, the Guy Medal, the Morgeson Gold Medal in Applied Mathematics. He does stuff on data science and biostatistics and computational biology and pretty much anything that is related to statistics. So today he's going to talk about computation, efficient, accurate statistical estimation, which I'm sure will be very interesting. And then we will try to put questions till the end. The floor is yours, Professor Fan.
Oh, thank you, Roy. So it's really a great pleasure to talk with colleagues at Brown University. So unfortunately, actually, due to various reasons, I haven't been able to go there. About 10 years ago, I was invited there, but then due to flooding in my area, so I got the basement flood. I think succeed going there. Roy, thank you for a very nice introduction. So the part of the reason I chose this topic is this. I think this seminar series is supposed to be like data science that connect with privacy. So that's actually part of the reason I give a talk on this, and hopefully that actually help. Contributing to the study of privacy issues. And I would also like to thank Roy for such a nice introduction. Really, all those introductions can be summarized in one sentence, right? So it is really data science that drive all those different research that I have been doing. So, here is the the outline of my talk. So first, I'll give a brief introduction just to show where we are, right? And then talk about disputed estimation if each local server or each study center has large enough samples. And this will be more algorithmic studies. And then regarding algorithm as a statistical multi-step estimator, I'll give you some statistical properties. And then I'm pretty sure most of people say, hey, we are in very different situations. Sometimes local study centers has only very few data points, so it doesn't satisfy your requirements. So how would I do it? So the fourth one, I'll talk about the dispute estimation in general regions. And finally, I give some numerical studies. So the work is based on two of my PhD students. Yongyi is, I think, 5th year, and Kaizun just graduated. Just tell me yesterday, last week, he taught at Columbia. Okay, so here's the introduction. So what is the common feature of big data, right? So we know that big data now is everywhere. Internet big data, medical big data, biological science, right? So government, digital humanity, and so on. Right? So they come in big volumes, fast velocity, and in variety. Too. So this certainly has a huge impact on system and analysis, right? Such as storage, communication, computation architect, as well as analysis such as statistics, computation, optimization, and privacy. And this is my view, right? So I always think, what is data science, right? So the collective efforts trying to solve these system and analysis issues, right? So engulfed by application. I think data science consists of data acquisition and storage, data analysis, as well as scientific computation. And whatever you describe, right? So the big data is always, data science always trying to turn big data into small data so that we can make decisions based upon. Now, since data science is is a field. So people naturally ask, what are the common features of the data science? And to me, the common features include, something that pandemic to big data, like dependence, because you measure many similar metrics, like let's say microarray or macroeconomic time series. In that case, you measure the economic health, right? Heavy tails, when you collect so many variables, you cannot assume data are Gaussian or something, right? And then heterogeneity, certainly occurs. This was one of the big issues, and one of the important issues in big data studies, right? Precision medicine, precision services, all those relate to study heterogeneity issues. And then, of course, endogeneity, spurious correlation also appears in the big data. So this is the feature of big data. And then, of course, data reality, right? So like many studies, when you have big data, you have missing data issues, measurements errors, survival bias, sampling bias, and so on, right? So my talk today is mainly on the last part, communication and computation, ownership and privacy issues that actually somewhat related to, to the theme of this seminar series. So here is the disputed estimation that I have, I have in mind, disputed learning. So, so first, I assume that data is stored in M different servers, and this M different server can be regarded as M hospitals, right, or M study centers. And for simplicity of notation, the idea applied to, of course, different data size. So I assume that each server or each study centers has a homogeneous sample size, little n, right? Capital N is the total data. And then, so these are the local machines or machine associated with each study centers. And then here is the typical, disputed learning, right? So each machine, let's say hospital 1, study center 2, hospital 3, and so on, right? So computing that, their summary statistics at the Tth round, right? So at each round, they compute summary statistics, computer summary statistics, TK, and then communicate with central processor, right? And the central processor just aggregates all those, disputed computing, and then, communicate back with each of those, of those local server. So this is really the disputed learning setting. And what is the goal of this setting? One is communication efficient, right? So we want the communication should be efficient, and the statistical estimation should be accurate, right? And the way that we are talking here actually at least partially summarize the privacy as well as ownership issues of the data. And the main reason is that we do not communicate many rounds, and we only communicate summary statistics. So therefore, there are very little, loss in between of this disputed learning framework. And also our assumption is like local computation is much cheaper. Indeed, communication within local machines could be 1,000 times faster than communication over the internet. Right? So the computation in each machine we assume to be much faster. So one of the example people could easily think of is right. So now the question naturally arises is what to communicate, right, and what to compute at each node, and then how many rounds of communication we have, right? So our goal, as I said, is communication efficient. So therefore, ideally, for big data, we do not really send the matrices, right? So we only send vectors to the central server. And we also want statistical accuracy, even though the data is disputed in, let's say, 10 study centers. I hope the statistical accuracy will be as good as you own all the data, as good as our goal, as if you own all the data. So this is our goal. By sending vectors to the central machines, we hope to gain the statistical efficiency as good as you own all the data. And of course, the study has a lot of literature, in statistics, like dispute estimation and inference, from M estimation to principal components to non-parametrics. Some are high dimension, some are low dimension, and so on, right? To the optimization communities, like dispute optimization and so on. So there are way more references than I can talk here. But if you really look at our main paper, that contains even more references. Right. So one of popular algorithm, or the first algorithm you and I could think of is so-called the divide and conquer algorithm. So which is very similar in a sense to the meta-analysis, right? So, for example, each local machine has their own data. You calculate your MLE, maximum likelihood estimator, right? And then you calculate your maximum likelihood estimator, and so on. So everybody calculate their maximum likelihood estimator and communicate to the central server, and central server just do aggregation, right? Could do median or could do mean average of all those, right? Or if you are talking about communication, the eigen principal components, the central space could do some kind of aggregation in eigenspace domains, right? So the strength is help solve privacy and ownership issues, because you only send an MLE, and the incentive maybe I could give you is when I aggregate everything of the study, I'll tell you what is the aggregated results, right? So this is so everybody everybody only communicating MLE to the central server. The weakness is this, right? So you are doing MLE based on this, right? So if I have 100 data points, then MLE's accuracy would be 100 data points accuracy. When you do aggregation will certainly reduce the variance. So in other words, when you do aggregation, so the variance of estimator would be as if you own all the data, because averaging further reduce the variance. However, the bias, right? So based on 100 data sample, the bias would be the bias based on 100 data points. So when you do aggregation, so the bias will be dominated by those local machines accuracy, right? Statistical speaking is if I have a little n sample size in each machines, right? And I have p variables, the square root of this should be the order of statistical accuracy, right? And then bias typically is in the second order, is the square of the square root. So this would be the bias. But we all know that bias cannot be, cannot be averaged away, right? So, so therefore, one step, or the quick divide and conquer algorithm, a little bit too simplistic. But nevertheless, let me first summarize the result for the divide and conquer estimator. Right. So for divide and conquer estimator, I call theta has 0. So its statistical accuracy will be consist of bias. Bias, as I said, is p divided by n. It is governed by each local machines. And the variance is p divided by capital M, because average or aggregation reduce the variance further, right? And then this step is just related to some kind of maximum error in your technical proof, but basically is a compromise between these two parts. And these are the dominant thing anyway. So now the next issue people naturally ask. So one step, everybody send the result to the central server is inadequate, right? So then why don't we do iteration once more, right? Or iteration twice more, or iteration 3 times more, right? So this will become one step or multi-step. And the purpose of iteration, from my point of view, is to do de-bias, because variance is already optimal, so you want to reduce the bias. Now, again, the issue you may ask is what to compute at each node, right? And then if I do compute this way, so how does performance changes over time? Can you give me a kind of description. How can I improve the performance? And so our main goal or our key message at the end of the day is that by using statistical methods, we could reduce optimization error very fast. So optimization error is the distance of your current estimator to MLE, as if you own all the data, right? So optimization error can be reduced by this. So therefore, not that many steps is needed for you to achieve the full statistical efficiency, right? So now when I say a factor like this, P divided by N, there are certainly two scenarios, right? So one is large local sample size. So this guy will be very small, and the other is small local sample size. Maybe this one is not small. You need to invent other methods to make sure all data being used and efficiency and the algorithm is converged. Okay, so now let me begin with our methods, is what to communicate once you have a good initial value, or even you don't have good initial value, you're just starting from zero, right? So what to communicate? And our key message in this section is gradient enhanced loss or gradient enhanced likelihood, depending on you're talking about least squares or maximum likelihood, right? So again, this is the setting. Total, if I aggregate, let's say 20 study centers, I have capital NIID sample, and those NIID sample is distributed over M different machines or M different, study centers. And what we are really interested in is the population risk, right? So the minimum, or maximum likelihood estimate, or minimum of the loss function. So, and let me use the theta star to denote the minimum. So in other words, this is the standard statistical problem, right? So I have data, I have a likelihood function, and or a loss function, and I want to estimate the parameter that minimize population loss. And this is the typical statistician are doing, right? So if I have n data points, I compute the likelihood or the loss, the empirical loss, right? So this is my fx, and then I put some penalty, right? So this is, so in other words, you are doing the penalized likelihood or penalized least squares. So this would be, the first part is the loss function, and the second part is penalty, right? So the loss function, since I assume each have the same data, is the same as average of the loss function in each study centers, right? And each study center is the likelihood function is just adding all those data together and just normalize by the size of the data. So in other words, this is the standard. So what is different from the usual statistical studies is that this F, right, had never been available to you. This G penalty, if you do L1 penalty, is L1. If you do L2, is L2. It's known to everybody. But without knowing other study centers data, I cannot compute MLE, right, or this FX. But each local machine can compute their own MLE. So this is the study, right? So example I have in mind is penalized least squares or penalized logistic regression. This could be lasso, could be shrinkage estimator, and so on, right? So rich estimator and so on. So this is the study. So the only thing different from usual is that I do not ask each study centers to give me the data. I only ask you to cooperate on a few steps of computation, right? So now suppose that I have a good initial value, which in my mind is divide and conquer, but that could be 0 too. You could just initialize from anything. Actually, our study applied to everything, but for understanding purpose or for most of the time, I was thinking this is the divide and conquer estimator. And then I can always approximate my empirical loss or my likelihood function, fx, by doing just simple linear, simple Taylor expansion, right? So this is doing expansion at this initial estimators, right? So this is, and this guy is a linear function. You just need to communicate coefficients, right? So linear function is always very communicable. Now, this is the approximation error. Right? So this is the true likelihood function. This is the linear likelihood function you constructed. And this residual, of course, is not available to any machine because no one ever get this F, right? So the residual function is not available. This linear function is available because I can communicate. I could send to each study centers this vector, right, intersect the gradients vector here. So what should we do, right? So if you do not know this, so the natural way is to replace this global approximation function, residual function, by the local ones, right? So this is the local machine defined similarly, right? So this is the local likelihood. This is the local linear approximate. I mean the first order approximation in the kth machines, right? So in other words, I just replace the function that not available to you. This is the residual by using my local version of the residuals, right? Now I'm adding these two together. At the kth machine, I have global, linear function from this approximation I put here, and then plus my locals residual approximation error. Right? So if I add in these two together, a very simple algebra is really the same as your local machine's likelihood, that is your study center's likelihood function, plus this term. This term is minus your machine's gradients vector by adding the total gradient vector, right? So in other words, so there's only one enhancement here, is the gradient vector in my machine is replaced by the average of gradient vector of all machines, of all study centers data. Right? So this is why we give a name called gradient enhanced loss function that we give a name here. So it's depending on, of course, two things, right? One is where you do local approximation, right? What is the initial value you are using here, and then of course the argument theta, right? So once I got this function, now what I should do, right? So I would do maximum likelihood, right? So now I minimize this gradient enhanced loss function. So this is the one that we are doing. So the good thing of this gradient enhanced loss function is you need only to communicate gradients, right? So I only dispute this vector to each machines, right? And the good thing is and then after I doing this, right? After I doing this, I maximize, right? So I minimize this guys, right? But because this is now my new loss function, is just replace my likelihood function by replacing the gradient compute based on my local data and gradient compute by order data, right? So I will minimize this. So let me call this minimizer depend on my initial value and the kth machine by psi theta bar, right? Then really the whole algorithm we are doing is really like this. You are keep iterating, given theta t, you compute theta t plus 1, given theta t plus 1, you compute theta t plus 2. You keep iterating this. And it's very easy to show that if you are iterating this, the theta hat, the MLE that we dream to have, right? So if I have all the data points, I will be able to get my MLE. So the MLE you dream to have would be a fixed point to this problem. So this is a fixed point to this problem. And indeed, the fixed point is very easy, 2 lines just to to verify. But I know we have a lot of materials. I'm probably not going to do this, but it's very easy. Just by definition, this is your gel function, and now you just take derivative and check the first order condition. The first order condition does obtain when theta hat equal to theta. So it's very easy to see is a gradient point. So this gives us the first algorithm. This by Michael Jordan and his collaborators is communication efficient surrogate likelihood function. So which is really the same thing that I was talking above. And this idea actually appeared earlier in this paper, right, by Shimi and and others. So the basic idea is like this, right? So you give me an initial value, a good initial value, and then you tell me how many iterations you want, how many step estimator you want, right? So at each round, each machine compute their local, gradient on that machine at that point, theta t, right? And then send to the first machine. And the first machine acting as a central server, right? So aggregate all those gradients sent in from all the study centers. If you think about it, or all the study centers, you just average of this. And now you do gradient enhancement, right? So this is the likelihood function in your first machine. This is the penalty, right? And then you just replace local machines gradient, right, by the average of the gradients, right? So this is really the gel function in the first machine, and then you just iterate. So in other words, every time each machine sends in the gradient to the first machine average them, and then just solve this gradient enhanced likelihood function, and then you get your next step, and the next step you could communicate with each machine again. So this is really the algorithm that I said, right? Starting from initial values, each machine, right, calculate their gradient vectors and send into a local machine, and the local machine solve the maximum likelihood function problems, gradient enhanced maximum likelihood problem here, and then communicate back. Each machine again compute a new round of this, right, and so on. So this is so if you're really thinking about two-step estimator, right? The first step estimator is divide and conquer. Each study centers calculate their MLE and they send to the central server, and then the second, the central server to the first machine. The first machine first machine tell you what is divide and conquer estimator. So each machine here now can compute their gradient at that point, and they communicate to the machine back, right? The machine calculate gradient enhanced maximum likelihood estimator, right? So when I describe this, naturally people come up with the second algorithm, right? Why do I let all other machine idle, right? So this naturally come to the next algorithm, which is a small improvement. We give a name called GEL, right? Gradient enhanced algorithm. So even though we come up with the same, the first algorithm we come up with the same as Michael Jordan and his collaborators, but our motivation actually is very different to get there. So this is the algorithm that we have, right? So it's like each machine sending gradient vectors to the central server, central processor, and the central processor compute the average of the gradient, right? And then broadcast back to all machines. So now all machines can do their gradient enhanced, computation, right? So gradient enhanced computation and send to the central server. And then, so now everybody now calculate their MLE based on their local machines, or gradient enhanced MLE, and then send to the central processor, and central processors just average them, right? So again, this iteration is really, mathematically speaking, you are really applied this dynamic iterating system. And since theta hat is a fixed point to each of those k, so of course theta hat is a fixed point of this algorithm with averaging, right? GEL algorithm with averaging. Okay, so this is our algorithm. Now, natural question we ask, okay, any algorithmic or statistical properties that you can tell us, right? And then, of course, we are here assuming data is large enough. If data is small enough, maybe local machine cannot even calculate MLE, right? If dimension is too high. So how do we deal when sample size n is small? So let me begin with large sample size, right? So I assume throughout, right? So the total data I have is enough for my study. Strong convexity, right? So this is the all study centers data plus penalty has a unique minimizer, let me call theta hat. And I assume this is, the loss function is strong convex in a compact region centered at the theta hat with radii r. Right, so this is a ball centered at theta hat with radii r. So this is the global strong convexity. And in addition, since I assume each local machine has enough data, so I assume local machine is also strongly convex, right? So each study center has enough data first, and then it's also strongly convex. And the radii, let me call C, right? So the smallest radii, I give a name called rho 0. Rho 0 is just strong convex, the smallest radii you could have strong convexity in your, the smallest minimum eigenvalue that you want to have for strong convexity. So this basically requires all sample size to be large. And then the second one, we actually using this homogeneity, that different problem from usual, optimization development. So we rest on the homogeneity. The hashing matrix based on kth machine and hashing matrix based on all the data. So the difference of them usually is the accuracy is governed by this, right? So this one is far more accurate because they all converge to population quantity. So this one I give a name called delta, right? So delta is govern the accuracy of this, right? For all machines in this box. And we know that in statistics, right? So this assumption typically hold with a very small, we'll characterize what this delta is and under very general conditions. So this typically, hold. So these are the two conditions. The main condition still is here. Local data is big enough so that I have strong convexity for, each optimization problem in each machines. And this is the first result, right? Deterministic result, or in probabilistic terms, so almost sure convergence result. So this basically is saying that starting from any values, the algorithm is converged to global MLE, close to global MLE in the rate of delta divided by rho 0. Rho 0 is the strong convexity, right? The minimum strong convexity among all study centers, right? All servers. And so this is a strong contraction result that we have. So if you iterate this, you'll get a strong convexity. And in addition, if we have hashing smoothness, that means penalty G have to be smooth. Then if we do iteration with average, that is using all the machines, the contraction rate is an order of magnitude faster. This is the part the same as this part, and then there's another part from here. So in other words, average does help. So let me just quick summarize. The CSL surrogate likelihood, less other machine idle, while one machine optimized, right? GEL run all the machine, and we basically shown that averaging reduce the variance. And more concisely speaking is that under some kind of hashing smoothness, one step of GEL of our method with averaging is almost as two steps of CSL, and the contraction will be a factor smaller. And if you don't have any smoothness and you're still doing averaging, I think it will not deteriorate any of statistical results. So this is basically give you an optimistic contraction. So now let's, so the proof actually is also not that complicated. So basically rely on first order condition plus strong convexity. But since now we have a lot of materials, I think I skip explaining how this was proved because there's a lot of material, particularly if I'm not working in this area. But I think this one, I think most of us will know. And this is the key point I want to show, and then we'll further generalize the result to apply to all the cases. What if my local machine do not have many data points, right? So this is the multi-step estimator and statistical analysis. So, and the key point at the end of the day, as I said, the optimization error will be contracted by an order of magnitude like this. And the key for proving this is I need to calculate the delta. What is this delta? Delta is this, right? So I need to calculate delta for a statistical problem. What is the rate of this delta? And then my rate will be contracting in this way. Okay, so so now let me begin. So again, we cannot be too general, and in order to get a result correct, so we can only focus on generalized linear models. So this is the generalized linear model we are familiar with, exponential family with canonical link. And I assume there's an intercept and there's covariate. Covariates are IID with mean 0, and covariates covariate have covariance sigma. And I assume this is Gaussian. So the covariates are Gaussian, and these are bounded, and theta star bounded. So these are all technical conditions. So under these conditions, we can show that delta, which is the hash matrix of each local machines, deviate from global's right, hash matrix. So you can always put a population one here, adding one and subtracting one. So it's really the accuracy controlled by local machines. So this one we can show is of accuracy P divided by N is local machine size, right? And this is the largest eigenvalue of sigma, operator norm of sigma, and this is the log n because we are talking about maximum errors. Right? So with this result, we can summarize our result as follows, right? So if I let my eta to be P divided by N, and then this kappa defined like this, like condition numbers, okay, then both of our CSL and GL algorithms in algorithm 1 and 2 will contract in this rate, and this eta will be very explicit. If we forget about other factor, it's really square root P divided by N, right? So it will be contract like this. And now if you have a Hessian smoothness also hold, then after certain iteration, you can say that gel will be like one step of gel will be like two steps of CSL. So in other words, average does help you get faster convergence. So now I think discussion of implication probably is better at this point, right? So first of all, each iteration reduce optimization error by approximately this factor if I assume all other things are constant. And at T step or iteration, you can always, the statistician always would like to regard it as a T step estimator. So the optimization error would be like T divided by 2, right? And now, so long as this guy converges to 0, that would be very fast, right? So optimization error would be quickly smaller than statistical error in finite step. Right? So because if this capital N is not too big, so every time you just reduce this by a factor, not too many steps, in finite step, you can easily achieve that the optimization error is below statistical error, so that you don't really need to optimize further. So this can be done under the very weak condition. And in addition to compared to like Jordan's methods, our result actually allows for 0 as an initial value, and also give very explicit rate of convergence or contraction rates. Now, probably for people like talking about privacy or talking about more applied, people naturally asking this question, right? So let me do this. So if I starting using theta 0 as divide and conquer, this is very natural. So you got an estimator. And this estimator, as I said, probably is not accurate enough if local sample size is not enough. So now I will naturally, using my gel, iterate one more time, right? So they give me a two-step estimator. So in other words, starting from initial efficiency, and now I do two-step estimator. Two-step estimator, we improve the bias, right? I mean, by a factor like this, right? So now the natural question you ask is, how big is the local sample size N is enough to make my bias is smaller order than statistical errors, right? So, and I calculate explicitly for you. So it's really just capital N to power 1/3, right? So long as your local sample size is of this order, it'll be negligible. And if you ask me, how about I do 3-step iteration or 4-step iteration or 5-step iteration, right? So each iteration, I will keep reducing optimization errors. So therefore, I will require less sample size, right? So and the result, of course, can easily be computed. That if you do T-step estimator, so the condition here become very weak, 1/n divided by T plus 1 here, right? And in addition, if you don't like convex optimization is easy. You just run gradient. If you don't like convex optimization, you can always replace by local quadratic approximation, as in Biggle paper. There's only one thing that I haven't talked yet is in more realistic situation, in most of our statistical applications, local sample size, each study center does not have enough data, right? So if I do not have enough data, everything I say here will not be valid, right? So all my assumption is on the local machine has strong enough data so that you have strong convexity, and that strong convexity will be destroyed if I have too few data points. And this leads me to talk the next level of distributed estimation in a very general issues, and we give a name called communication efficient accurate statistical estimator. Okay, so as I said before, the difficult in general region is local machine may not have enough data to enjoy strong convexity. And the delta, the discrepancy, right, the measure between Hessians may also big enough so that doesn't contract too fast. So, so now if you don't have enough convexity, so how do people do, right? So people usually do adding a quadratic function to it, right? Quadratic function is always strong convex. So it's an isotropic quadratic, right? So this is what we do. And the methods in optimization literature called proximal points algorithms. Right, so this is loss job plus penalty that we have. Now I'm just adding just like a ridge regression statistician would call, right? So this is ridge, of course, depend on previous iteration theta t there. Right? So other than that is really the same, right? So once I add in this, right? Once I add in this, now this is a strong convex, there's no doubt, and I add in current iteration to this, right? So it's a strong convex, it's shrinkage towards theta t, right? So now, however, I cannot calculate this estimator because this guy is not available to anybody, right? Because this is the likelihood based on all study centers. So I don't really have this likelihood, right? But this problem is a disputed problem too, right? A disputed computation too. Now, if I do apply the organs that we just mentioned at the beginning, and the previous the talk that we talked before, then I have to run one iteration, and then I have to do another iteration over t here, right? So in other words, I have to apply disputed computation to this. For each given t, I have to run this until convergence, and then move t along. So I will have double loop. So this will make a problem, right? So each step is a dispute optimization problem. So if you really do computation and run all of this, you have double loop. That will be too expensive. So, but instead we only run one step of the algorithm. So this make our computation much simpler, but analysis will be harder. Okay, so here is the algorithm. So let me summarize. We call communication efficient accurate statistical estimation. So you determine the number of iteration you want, right? So at t step, you ask each machine to calculate the gradient and vector and send to the first machine. The first machine average all those gradient vectors, and the compute is gradient enhanced loss function, right? And now I add in the quadratic term here to make a strong convexity, right? So now I'm only do this for one shot. I didn't do any computation, and then just broadcast this result back to all machines, right? And then if I just keep doing this t times, I got the t-step estimator. So in other words, in each of computation of this gradient enhanced loss function, we only do one shot. We only do one step computation. So in particular, if this alpha equal to 0, you do not put any proximal point or quadratic function here. This is correspond to CSL we talked about before. And of course, this is let one machine run. You can also let all machine run. So it's the same algorithm. To save time and discretion, I just say, hey, algorithm 4 be the same like this algorithm, but I would do send all results to each machine. Each machine calculate their own version, and then log to the central server. Central server will average them together. So this is the estimator. Now, what is the result? So can we achieve the convergence in any scenario? The answer is yes. So if I take the alpha, like a regularization parameter or proximal point parameter, alpha large enough so that this hold, right? So this, when you take a large enough alpha, this one always hold, then we basically say both algorithms will contract by a factor strictly less than 1. So this is the contracting factor. The first factor is reflect the inaccuracy estimation. When we do distributed computing in each step, we are lazy, we just do one shot. So this is the contracting rate is lower by this much. And the second term here is exactly to proximal points approximation. So in other words, for any sample size, by doing this, you always get a convergence, right? So if you have hashing smoothness and you run the algorithm with average, so the rate will be improved. And the improvement is this one here by this gamma t. It's a little bit ugly, but it does improve the algorithm. So let's add a discussion. What is the alpha? Ideally, what is the regularization parameter alpha I should put? So first of all, so long as alpha is very large, right? So both algorithms will contract by a factor at least like this. So you'll be always contracting by a constant. Every time you reduce bias by a constant, so you need logarithmic order of iteration to do it. But however, when this guy is small, right? This is the homogeneity parameter, hashing matrix homogeneity parameter. When this one is small, then you take, if you take alpha of this order, then you can see the contraction rate still like this. So in other words, if you look at this, big, you always contract. Small, if you take this order, it's also contract at optimal rates. So this leads us to the conclusion that what the choice of alpha is of rho square, delta square divided by rho. So in this case, you'll get a fast contraction for large sample size and also guarantee convergence for all the cases. If you don't have enough local data, you still guarantee the convergence. So now, if I summarize the result for generalized linear model, what we just really said is if I let delta like this, if alpha bigger than this, then both algorithms always converge, right? So if alpha less than this, there is contraction at a rate of this eta is a rate, as what we say before, p divided by n. So this is a statistical result for generalized linear model by combining all the results we have so far. So let me just quickly remark, because I think the word here probably easier to understand, right? So in the large sample regions, so if you take delta is not too big, right, just the right order, then the algorithm always have a very fast linear convergence because you are just choosing the right order. It will not destroy benefit small alphas, right? And then you also benefit from homogeneity and you speed up convergence. And under the general regions, if you take alpha also of this order, you can always guarantee linear convergence and adapting to all different local sample sizes. And naturally people ask, hey, what if I do least squares, right? So the whole problem I talked about so far, it could be just least squares. And for the least squares, every step function that I write there would have an analytical expression. I could easily write down for you, but I thought it's probably not helpful. It's in the paper, right? And then of course I can also guarantee stronger rates of convergence. So for example, in the least squares, I have a neater type of results, and the contraction rates looks like this, is much simpler. And the condition number that I have here for the least squares doesn't come into the rate, but condition number is a constant in front of it. So you can calculate, so the rate of convergence does not depend on kappa, and this improve all the previous results in the literature about this problem. So the contraction rates is very analytical depending on all these. Okay, so these are all the theory. So let me just, for the last, let's say 5 minutes, let me finish in 5 minutes to give you some numerical studies. Right, so in the numerical study, the first one is distributed logistic regression. So I have, what I have is, I have 10,000 data points and 100 variables, and I have theta hat is uniformly generated from here, right? So my variable is basically based on Gaussian covariates, and now I divide 10,000 sample into 3 different scenarios, right? One is into 5 study centers, so each of those have 2,000 data. So I look at the first panel here as the large sample situation, this one as a moderate sample situation, and this one is small sample situation. Now I have, many methods, right? So I have C's with proximal points, and I could have C's without proximal point. That is, take alpha equal to 0. I could do average. I could do without average. That give me already four method based on our own. And of course, I can also compare with in the literature called Giant or ADMM or accelerated gradient method. So total, I have 7 methods. So so describing this is accelerated gradient method. This is ADMM. And now what is up and down here is good initial value using divide and conquer as an initial value. And the panel, the row here is using 0 as initial value. So among those, our method that we want to, key method we want to say is the red curve. So it's the red curve always converge very quickly to below statistical errors. ADMM, and this is not, right? So in contrast, the CSL, that is use alpha equal to 0 without proximal points. And in the local data case or moderate data case, it can even diverge, right? So the green here can even diverge in the small and middle case, data case. And here is the L1 regression. So you do penalized logistic regression. Again, I have 5,000 data points, 1,000 dimension, and among those 10 are non-zeros. And now I do L1 regression, L1 penalized L1. And in this case, I have only 3 methods, ADMM, and 4 of our own methods. Again, you can see that our methods is always converge, and they converge faster than ADMM. So this is another iteration, and this is just a real data just to show the divergence issue does exist, right? So this is like email spam data, have 4,600 data, and the 36 as a training data, and that's what we use. We divide into 5 machines, so it's be 720 each machine, 360, right, 180. And in this case, the number of variable is 57. Right? So this is moderate sample, small sample, and this is large sample. And all our methods, the red one that you are looking at is very converge very fast. And of course, blue sometimes work better if I have large sample as expected. But on the other hand, like CSL without regularization would diverge, right? CSL would diverge. Giants also and all other methods would diverge. Anyway, so let me just summarize the numerical results as well as the whole talk, right? So we basically saying that with proper regularization, our proposed 2Cs algorithm with averaging and without averaging always converge very rapidly in all cases that we experimented. And the average always outperform because you're using all the machine computation powers. Deterministic method like ADMM or accelerated gradients are also reliable in the sense that converge, but they are converge much slower because it doesn't take statistical homogeneity into account. Other distributed algorithms like CSL, giants, or unregularized Cs often fail when sample size n is small or when the initial value is 0, inaccurate. Okay, so the conclusion of my talk is as follows, right? So the C's methods are communication efficient, take advantage of large sample size and the power, and the power of local averaging. It can handle both smooth and non-smooth loss, particular penalty part, and cases with both large and small local sample size. It poses minimum assumptions on initialization and converging very fast when you do a warm start, when you do a good start. And we show that starting from divide and conquer, we tell you exactly how each step improve the bias. And we basically saying that by doing 2-step, 3-step, bias could easily go away within a finite step. And by introducing a proximal point parameter there, or a ridge regression, statisticians like to say that way, but then you make the problem convergence in all settings. You just sometimes you have a safeguard for your analysis to converge as good as if you own all the data. And that's all what I want to talk. And this is the paper that I will talk about. Thank you very much.